July 1945, Alamogordo, New Mexico. Watch the first atomic detonation in history. Operation Trinity. The long series of nuclear tests is underway. July 1946, Operation Crossroads. Bikini Atoll in the mid-Pacific. The war over, scientists and military personnel busy themselves setting up a target of ships for the first peacetime test of the atomic bomb. High-ranking military personnel and civilian observers watch the able shot. 19 kilotons burst 516 feet above the surface of the lagoon. Damage to the target array is assessed and preparations are underway for the Baker shot. The bomb, similar in type to the Able test, is located in an airtight caisson beneath the surface of this tropical lagoon. With all preparations made, Baker shot occurs on schedule. Many impressive and startling effects are observed on this shot, including the first appearance of a base surge, seen here enveloping the target ships. April 1948, Eniwetok Atoll in the Pacific. Our third nuclear test program gets underway. Operation Sandstone. 3 weapons, fired on 200-foot towers, with batteries of scientific instruments to record results. As at Bikini, drone planes are used here. Giant planes, heavily instrumented but without crews, take off to fly through the heart of each atomic cloud, to collect samples of that cloud for detailed radiochemical analysis. Three times the sound and fury of atomic detonations shatter the Pacific dawn. 3 times a scientific laboratory is created to study previously unattainable effects of high temperatures and pressures. But what did we learn from these detonations? What were we trying to prove? Why did we expend this almost priceless nuclear material and these thousands of man-hours of labor? Let the men of Los Alamos give us the answers.
We returned to the Hill from the sandstone tests with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, pit designs, core arrangements, initiators. Information that would enable us to increase the small percentage of active material that actually burns during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive, the elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive force, and that the implosion principle was sound. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonations, the effects from an atomic explosion became of prime concern to the armed forces. Thus, Crossroads using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Able and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory research, in the meantime, developed new weapons for the sandstone tests. At Sandstone, we were once again able to tackle the big problem, more efficient use of fissile material. Here, we were able to utilize uranium-235 in an implosion-type weapon. As time went on, we had increased our knowledge of weapon design and had, therefore, increased yield per kilogram of active material. This is where we stood by the end of Sandstone. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as J Division, is organized. Dr. Alvin C. Graves is selected to head this division, a unit with the specific job of testing weapons. By autumn of '48, a test program is framed. This calls for experimentation of new weapon designs with the objective of again moving our knowledge curve upward to a more effective level. Once more, we propose to better yield per kilogram invested. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon. These are the main objectives in the weapon development field.
And so Operation Greenhouse gets underway, with Eniwetok designated as headquarters island for the Pacific Proving Ground. Engebi, Runnet, and Eberiru are the shot islands. During late 1950 and early 1951, work progresses in the islands. Towers are built. Recording stations are constructed. Coaxial cables for the shot towers are laid. Myriads of instruments and intricate wiring hookups are checked and double-checked. Finally, everything is ready for the biggest job in nuclear testing, the job of obtaining exact information about the detonation itself. The builders are through, and the scientists take over the story.
Those of us from the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into two major areas: diagnostic testing and effects testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effects tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, three kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time; the rate at which the chain reaction multiplies, alpha measurement; and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of the nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HE system, is cabled down to a recording station and measured by sweep oscilloscopes. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between the impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomena. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fissions in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons, 1 kiloton being the force released in 1,000 tons of high explosive. One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield per fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shot time. They will travel in a long arc and pass through the cloud at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself.
Shot number 1, dog. The objectives of the test of the Howe weapon were to prove a weapon of higher yield and efficiency than currently stockpiled. The predicted increase of efficiency made possible by the Type D pit was confirmed. Shot number 2, easy. The objective of the test was to prove a lighter and smaller weapon with acceptable efficiency. The feasibility of obtaining acceptable efficiencies with lighter and smaller weapons was confirmed, and thereby future weapons design was advanced. Shot number 3, George. A step was taken along the path to thermonuclear weapons by the achievement of a fusion reaction. Shot number 4, item. The successful booster reaction proved the feasibility of increasing fission yield by a limited fusion reaction and gave more impetus to the development of booster weapons. Fission weapons proof test. Physics experiments run on thermonuclear reactions. Military and civil defense knowledge immeasurably increased. This was the accomplishment at Runnet, at Engebi, at Eberiru in the spring of 1951. Once more, the Pacific Proving Ground has proved its value, but the job is far from complete. Each test series leads inevitably to new developments requiring still more tests, more frequent than are practical at distant NOE-TOC, where logistic problems make it difficult to run more than one test a year. We need a site much closer to home, a site in the continental United States. But where?
For a long time, as a matter of fact, ever since Trinity, men from Los Alamos had been eyeing the great barren stretches of the Southwest. This region, for the most part, fits the bill. Isolated from centers of population, with favorable winds, with the necessary consistency of soil and formation of Earth's strata below. And so beyond a World War II training base, to the north of an early-day Nevada stage stop called Indian Springs, 65 miles north and west of Las Vegas, an atomic range was established. A test site of over 400 square miles of flatbed valleys, mingled with mountains of solid rock, whose veins once colored history with gold and silver. A range remote from civilization, isolated, forgotten as the names of the men who once made their fortunes here. In the pre-dawn hours of January 1951, this long deserted countryside came once more into international focus with Operation Ranger, the test of 5 atomic bombs, 5 successful airdrops that saved the weapons research program months of time, considerable money, and helped Los Alamos prove the radical new idea of small atomic bombs. Soon after Ranger, another use of the Nevada test site was apparent. This was a chance for the military to get more information in a shorter space of time on the effects of atomic weapons. Vital facts. For what good are atomic weapons without full knowledge of what they can really do and how we can be protected against their effects?
Thus, Operation Buster was born. In the fall of 1951, the combined Operation Buster Jangle was held at the Nevada Proving Ground. Five weapons in Operation Buster. 1 on a 100-foot tower and 4 air drops. A tent city, Camp Desert Rock, was activated and occupied by observers from all the services, arriving here from all corners of the Earth to participate in an atomic maneuver. Here they receive extensive indoctrination by experts from the Armed Forces Special Weapons Project in the expected phenomena of the detonation, and by Camp Desert Rock personnel on the assumed tactical maneuver. Early on shot morning, they load into trucks and buses for the long trip to the target area. In the target area, last-minute orientation talks are given, and the observers prepare themselves to watch an atomic detonation from the closest point that personnel have ever been during nuclear tests. Following the detonation, the troops move forward to the ground zero area to inspect the effects of the bomb. Since the Ranger shots were experimental devices only, this was the first stockpile weapon to be detonated within the continental limits. Operation Jangle, immediately following Buster, was our first test of surface and underground atomic detonations, designed to study military effects of these types of bursts. Jangle number 1, the surface shot, heavily instrumented to study energy coupling in the Earth itself. This low-lying cloud is hot with radioactivity trapped in Earth particles thrown out by the force of the explosion. In a little while, ground monitors mark off the outer limits of personnel re-entry into the blast site. In the fringes and interior of the crater itself, the spot that once was ground zero, there are soil specimens of great value if they can be collected before their short-lived radioactivity dies. Remote-controlled Army weasels, drone weasels, are warming up for this collecting job. A compact television camera mounted on the front of each weasel will inspect the terrain as they go and relay the picture back to their guiding control station. Scoops on the front of one drone will gouge out and bring back surface samples of the crater dirt. A drill rig mounted on the back of the other weasel will bore down and secure cores, which will tell the story of subsurface radioactivity. Now the push is on for Jangle 2, the underground detonation. Like the surface shot, this will be a 1 kiloton gadget, but this time it will be detonated 17 feet beneath the surface of the Nevada soil. Very extensive military effects tests will be run with this detonation. Dummy buildings with superimposed loads to represent upper floors, and underground structures, such as fuel storage tanks, water systems under hydrostatic pressure, gas mains, and electrical mains have been constructed to gain realistic data on ground shock and cratering action. Inside the control point, members of the military effects test group supervise the detonation.
5, 4, 3, 2, 1, 0.
After the detonation, test structures are studied, and the many scientific and military personnel involved return to their home bases to evaluate the results of the operation. After the 7 shots of Buster Jangle are complete, the test area lies dormant, waiting, ever ready for future tests. Our proving ground. The bomb, similar in type to the Able test, is located in an airtight caisson beneath the surface of this tropical lagoon. With all preparations made, Baker shot occurs on schedule. Military personnel busy themselves setting up a target of ships for the first peacetime test of the atomic bomb. High-ranking military personnel and civilian observers watch the Able shot. 19 kilotons burst 516 feet above the surface of the lagoon. Damage to the target array is assessed and preparations are underway for the Baker shot. July 1945, Alamogordo, New Mexico, watched the first atomic detonation in history. Operation Trinity, the long series of nuclear tests, is underway. July 1946, Operation Crossroads, Bikini Atoll in the mid-Pacific. The war over, scientists, many impressive and startling effects are observed on this shot, including the first appearance of a base surge, seen here enveloping the target ships. April 1948, Eniwetok Atoll in the Pacific. Our third nuclear test program